That are soft matter. Polymers, micelles, suspensions, emulsions, foams, liquid crystals, and this may or may not mean much to you, but in fact, these are things that we encounter daily. So an example of a polymer solution is an engine oil, so that consists of long polymer chains in a short molecular solvent. Micellar systems, which are also polymer-like structures made out of soap molecules, are in nearly all brands of shampoo, and suspensions are toothpaste suspension, etc. I can go on down this list. So you can see why these are called soft matter. They're mostly pretty soft. But there's also a whole branch of physics connected with the kind of high-tech end of soft matter. So all polymers, all plastics rather, in processing go through a molten stage or a semi-solid stage. Additives very similar to what you have in shampoo are used in things like this oil pipeline down here. Pharmaceuticals, drug delivery, etc. Foams, foams get used in cleaning up after fires and things like that. And liquid crystals are in every single one of your laptops and mobile phones. So, the picture as physicists we can have of these systems is to back off from the molecular detail of exactly what's in there and try to classify them into broad categories. And then within each category we're hoping to find universal types of behavior, which does include the phenomena I'll show you later in this jar here. So polymers we think of as molecular spaghetti. Suspensions of colloidal suspensions, or these kind of dense suspensions here, are basically molecular ping-pong balls or microscopic ping-pong balls, small hard particles suspended in a solvent such as water. Liquid crystals are also like that. Then you have to think of them as needle-shaped structures here. So today I'll focus on the middle one, suspensions, the baseline model, molecular ping-pong balls, and how does the presence of this structure, the fact that I have some kind of organization of these solid particles inside my suspension, how does that control its macroscopic behavior, and in particular, how does it control the flow behavior, which, as we shall see, can at times be spectacular. So one of the main intriguing features of the flow behavior that we'll see is the presence of an effect like a traffic jam. It's a jamming phenomenon. And so what I want to do next is show you some other natural phenomena involving jamming and unjamming. So the top right is fairly familiar. Bottom left is actually a log jam, literally. You're in Canada, so you should know all about that, but most Europeans have never seen or heard of a real log jam. This is a landslide, and as you can see, this is something which was solid, but is now turned into a fluid. And obviously, if that happens near you, you need to get out of the way. This is only an animation, because this kind of thing, when it happens, you're rarely waiting for it with a camera crew. This is a grain silo, and this is something you really don't want to happen in your grain silo. It's to do with the build-up of stresses in the granular packing, quite similar, in fact, to the kind of thing I'll be talking about later on, and then a catastrophic unjamming in that final frame. So, on to the main deal, dense suspensions under flow. So, let me show you a couple of movies. Get them both running once. Okay, so on the left here, this looks like a computer simulation, but it's actually an experiment. So what's done here is you have these microscopic colloidal ping-pong balls, roughly 1 micron particles, in a solvent, and you're shearing them. So you have a moving plate across the top here, which is moving to the right, and a stationary plate at the bottom. You saw here a similar movie, this time a computer simulation in 2 dimensions. I'll show that one again. So you can see here this also, so the blue arrows here are showing you the average velocity. So you have this shear effect. But you can see this has a kind of stop-start motion to it. So the fact that this is an unsteady flow is all part of this jamming phenomenon that you get in dense suspensions. So the presence of this kind of behavior is actually quite mysterious, at least in terms of the standard way of thinking about these systems, and that the fact that it's the models we had until recently anyway were quite constrained as to what they could predict, and they could not predict some of the phenomena that I shall be showing you. So let's go to the baseline model of fluid flow, which is Newton's law of viscosity. So you can read about this in Latin, in trivia. So we have a stress. So if I have a moving plate and a stationary plate, I have a stress force per unit area horizontally on the top plate here. The displacement is r dt. So r is the strain rate, so that's the speed of this plate divided by the depth of the sample, and the area of the top plate is a. So Newton said, okay, the force is proportional to the rate of strain, in other words, proportional to the amount of shearing you're putting in. So S equals nu times r, nu, Greek letter nu. If you want to read that as V for viscosity, that's fine too. In the field, stress is usually called sigma, strain rate is usually called gamma dot. I'm trying to be a bit more sensible than that. So stress as a function of rate, strain rate, r. Newton's law says that stress is proportional to strain rate. So the viscosity is the slope of these lines here, and it varies from fluid to fluid, but in each case you have a straight line. So that is a class of behavior which is widely seen and is called Newtonian flow behavior. However, other things are also seen. So non-Newtonian fluids have a stress as a function of rate, which is not a straight line, and can have all kinds of curvature and variation. Various names, shear thinning, shear thickening. As you can imagine, those describe the case where the stress is curving downwards or curving upwards. And the case I'll be talking about is extreme or discontinuous shear thickening. So there are many examples of these. The ones on the left, water, olive oil, honey, molten glass. These are Newtonian. You might not think that about melted glass, but it is. It's extremely viscous, but Newtonian. Honey there, I mean the kind of runny kind of maple syrup, better example. These ones on the right, including saliva, the engine oil I talked about before, putty, molten plastic, these are non-Newtonian. These all have non-linearity in those curves. And the mystery is why the molecular ping-pong balls, the dense suspension, why is it ever non-Newtonian? Because the first pass theory seems to constrain it in such a way that it must be Newtonian. So that's part of the story I'm trying to tell. So, it looks like I'm getting through this talk very quickly, doesn't it? Unfortunately, I'm going to focus on how we explain it. So, shear thickening suspensions. Okay, so first though, I want to gather the phenomena. I want to tell you what it is that a theory should try to explain. Shear thickening suspensions are liquids that solidify at large stresses, hence the title. Ubleck, if you go to popular science web pages and many science fairs and all kinds of events and school lecture talks, which I give myself, Ubleck has become the word for this material. This is cornstarch in water here. I'm just about to show you what it does. Based apparently on this remarkable book by Dr. Seuss. So, in which the world is apparently invaded by a non-Newtonian fluid. I've not read this book, I'm afraid. I'm sure many of you have, but it sort of sounds a rather surreal nightmare. Anyway, let me show you some. So, what we have here is cornstarch suspension. So you go buy cornstarch, and custard powder is the same as cornstarch, it just has yellow dye in it and some sugar. Hence, bulletproof custard. I could have said bulletproof cornstarch, but that would be an even weirder title. So I'm going to drop this stick in here. So the idea is that this is a fluid if I'm very gentle. So I'm barely touching this. I can move the stick around. See, I can wobble it. It looks pretty runny, maybe a bit sticky. But then, a bit difficult getting the stick out. Let's try this. Okay, so this is an unusual fluid. I've actually smashed the beaker here, and it's not leaking out. But and this now you can also see this is it's gone in. Okay, so it's doing what I said in the title. If you're gentle with this, it's quite runny. If you're violent with it, it just resists. So as somebody who recently, for the first time, became the owner of a dog owners will know what it's like to have a dog that has a different view of where you're going on your walk from you. It doesn't matter. The harder you pull it, the slower it goes. So this is really the same. So let's be gentle. I'll try to be gentle with this first. But even now, you see, good. Let's leave that. Let's see what happens. So this may fall off at some point. Having already broken the beaker, I should later. So you see, there's lots of very interesting flow instabilities here. So what's happening then is that the fact that this is harder to flow when you push it hard has a bunch of phenomena associated with it. One is that the transition from being easy to flow to being hard to flow can be very sudden, and the other is that the resulting flow can be very unstable. And if you see how wobbly the front of this kind of sheet of cornstarch is here, this is not like the flow of any Newtonian fluid. Even if I slow down the movie, you just don't get this kind of instability. So let me see if this will stay without falling. Let's try and leave that a little bit longer. It's going to fall off eventually. Right. How are we doing? Ooh, what's that? Oh, I see. Yeah, well, I want to go back to my slides now, right? Oh, thank you. Yeah, so you can place your bets as to when that's going to fall off during my talk and scatter bits of wet loop all over the place. Okay, so this is the Daily Mail, one of the UK's most reputable newspapers, talking a few years back about bulletproof custard. So how it works, you can read how it works. Traditional bulletproof vest is made of laminated Kevlar, and Norman Wagner in the University of Delaware has got patents, and the US Army is developing bulletproof clothing which has much less Kevlar, and between each layer of Kevlar and the next is a layer of stuff very like this. So the idea then is that the bullet is like the hammer. It hits it and it solidifies, and that spreads the load out of a much wider area, so you can get away with much less Kevlar and much less damage when you're shot. So bulletproof custard is their phrase, but I was very happy to borrow it. And of course this isn't custard, but it is exactly what you get with custard powder if you put too much powder into the water. You'll also see things like this online, which is the same. This you need a lot of cornstarch, but it's quite fun if you can get it. And yes, there is sound on this movie. That's good, isn't it? There's sound on this movie, but I don't know what expletives that guy's uttering in his own language, so it's quite lucky that it is muted, in fact. And let's just see that again. So the first guy, you can see the whole movie, including this guy falling, sinking in, which is just like the hammer did. He just stood still for a while and sank. And if you don't stand still, you can run across the top. See, that's still going over there. So this is and this is now, look at the logarithmic axes here. This is the stress as a function of strain rate for a shear thickening suspension, of which this is an example, although that's not exactly the one in the picture here. And you can see that at a certain rate of strain, if I above a certain stress, about 10 Pascal, certain rate of strain, there's 2 orders of magnitude jump in the stress. So a huge leap in viscosity, and what's more, there's hysteresis. In other words, you go up on the right-hand red arrow here, and then if you back off So slow things down again, you come at a slightly higher stress and come back down a different curve. So that's a signature of certain kinds of physics that I will indicate in a minute, hysteresis. And if you look more closely at data like this, so this is actually data from this year from the group in Edinburgh that I'm still associated with and used to be in. So these are a bunch of flow curves, again, stress against rate of strain on logarithmic axes, and what you're doing here to go from one curve to the other is you're changing the concentration. And this actually is cornstarch, it's just like that. So that stuff there is probably about where the blue curve is. So there's a parameter which is the concentration. So the dimensionless measure of concentration is actually the volume occupied by the solid particles, a fraction of the volume of space in this solution that's occupied by solid. So number per unit volume times 4/3 power cubed if they're spherical, which of course cornstarch is not exactly spherical, but we know how to correct that. So this is a dimensionless number. It's important that it's dimensionless, but it's the control parameter which takes you from one flow curve to another. What you also find, though, when you look at this more closely, is that in these very vertical curves here, like the blue one, the flow is not there. Yeah? Now, I actually going to... Okay. So now I'm afraid I have to issue advice to the cleaners, and I'm sorry about this. There's puddles of this all over the carpet, but you just have to wait for it to completely dry, and then you vacuum it up. I'm sorry, I wasn't planning that quite that way. Okay, so right, yeah. So the flow has structure. It's not steady. So, for instance, if I take somewhere in the middle of this, in other words, if I take a sample like that one and I put it in a professional flow measuring device, which is called a rheometer, so I have a carefully designed machine with moving parts that I can measure the stress as a function of time, I get a curve like the thing on the left. So a ordinary Newtonian fluid, that would just be flatlining in time. It obviously has a stress that is proportional to the rate, but if the rate's held constant, the stress is not wobbling around like that. So that's another characteristic feature, and it's also what we saw related to this phenomenon here. So to say a little bit more about the movie, the red bars here are showing you the connections between particles and the forces that are carried between them. So in a computer simulation you can figure all that out. You can't measure it directly in an experiment, but you see what you have there is a network of forces which is coming and going, and you slow up and speed down according as to how well connected is the structure. So that brings me to the explanation. My computer says 1 hour, 36 minutes and 10 seconds have elapsed since the start of the talk. So this is a disadvantage of having it set up too far ahead. I shall switch to my watch. Right. So how do we explain this? Well, there is a phenomenological behavior in terms of the stress as a function of rate of strain, which, if only we could explain that, would explain this. So let me say what I mean. Here is a viscous fluid. These are called the flow curve. S of R is a flow curve, and for a Newtonian fluid it's a straight line. And I'm just increasing the concentration. If, as a function of concentration, I could get the following evolution of my flow curves, then everything you've seen would be explained. And this is increasing concentration here. If I could get the flow curves only to do this, then everything would be fine. And the reason is that these decreasing parts of the flow curve are mechanically unstable. So when you enter this kind of region of parameter space of stress or strain rate, you expect flow instabilities. You also expect sudden stress jumps for this reason. Oh, so let me do the instabilities first. So the dotted part of the curve here is unstable just for the same reason as a particle at the top of a potential is unstable. This will just split off to either one side or the other if I work at fixed rate of strain here. And you can think about the acceleration of a small piece of fluid in a regime where the stress is decreasing with strain rate. You can see that it's got a positive feedback and will run away in one direction or another. So the flow instabilities one can understand from the negative slope regions of these flow curves, and the hysteresis likewise. If I gradually increase my stress, or rather if I increase the rate of strain here, then at some point I can't go any further on this lower part of the curve, and this is all unstable, so I end up jumping discontinuously to the upper branch here. And again, these can be two orders or three orders of magnitude apart in stress. And then if I come down, I can experience a hysteresis loop which comes down to this back kink here. So that's all fine. In other words, we know exactly what the target is for our theory. It's flow curves which look like that one, or particularly the whole family that I described before. So let me explain why that poses a difficulty. So here's what we want to explain. Flow curves of this type, let's just take a typical one out of the middle. So all we need is a flow curve with a wiggle. Now, however, if there's going to be a wiggle, and I'm going to have a theory of it, I have to be able to tell you where the wiggle is. So if we think about dimensions, stress, oops, go back, mass per unit length time to minus 2. So mass length of time into the stress has the same dimensions as pressure. The strain rate is the rate of change of an angle, essentially, so that's got dimensions of 1 over time. So I have to somehow find some physics that fixes one of these parameters. And the problem is that if we turn to our standard model of dense suspensions, which is this microscopic ping-pong ball model, it turns out I can't do that. So let me just explain what the problem is in those terms. The solvent has a viscosity. So that has dimensions that we know. It's 1 factor of time times the dimensions of the stress. We know, however, as those of you familiar with fluid flow of any kind will understand from what I've been showing over there, that inertia isn't relevant at the microscopic scale here. In other words, the fact that these particles have mass is not important. The fluid has mass, the particle density and the fluid density are almost the same. This is not to do with accelerations. The whole of the flow of these dense suspensions is to do with the fact that particles are slowly pushing fluid around. It's all overdamped in that sense. So there isn't a mass coming from the particles either. They do have a size, well, that's big R, and they have some force between them, which in the standard model is basically a hardcore interaction. So the force is 0 until the particles touch, and then it goes straight to infinity. So that's the kind of simplification that theoretical physicists like to make, and in this field of suspension physics, that has got us a very long way. So 50 years of progress are based on that sort of model. But in this particular context, we have a problem. If I look at this, I can get a length from the particle size, but I cannot get a time. And if I look at that force curve, gain length from the fact that it sets in at 2r, but it's either 0 or infinity. So there's no scale connected with that either. So what I can't do is find a time scale which I would need to convert the solvent viscosity into a characteristic stress, S star. So I cannot, from this physics, I cannot make a characteristic stress or a characteristic strain rate, because that again requires the inverse of a time. So from this particle size, the fact that they're hardcore interactions, and the fact that they're in a solvent of viscosity nu S, cannot give me a wiggle, because there's no physics there, dimensionally, that can present a characteristic value of stress or strain rate to me. So that's a kind of slightly subtle argument, and it sounds like there must be a loophole. Well, of course there is a loophole, otherwise I wouldn't be able to go on with the talk, but it's a subtle loophole. So the question is, which of those assumptions has to go, essentially? Something will have to. But meanwhile, let's just recap that. Standard model, then, we have a system where if I have strictly hard particles in a solvent, then depending on the concentration of those particles, I can have a low viscosity at low concentration, or a very high viscosity at high concentration. Or in fact, if I push the concentration too high, the viscosity can diverge, and then I have a solid. But nonetheless, what I have in the standard model is either a perfectly Newtonian curve with a certain slope, or in the case where that slope is infinite, I have a solid. What I can't have is a wiggle or anything which jumps discontinuously from flowable to jammed behavior. It's either always flowable or it's always jammed. So that doesn't explain any of the phenomena I showed you. So nu is the viscosity of the suspension as a function of concentration, and it has the potential to diverge at a characteristic concentration, which is a key parameter and is something that holds in it the explanation to everything I have shown. So this parameter, this is called the jamming concentration for obvious reasons. So below Cj you can flow, above Cj you cannot flow. And an interesting question is what controls that concentration. And this is something which we've only very recently understood, and I think the entire community is a bit embarrassed by the fact that it took so long to understand what was happening here. But what you find is that the position of this divergence here, so the place where the viscosity goes infinite, where this curve goes vertical, depends on the nature of the friction between these hard ping-pong balls. And I never mentioned friction up to now, so that's the new piece of physics, but it enters in a specific way that I want to now explain. So yeah, so essentially this was kind of realized in a strange holographic way by a whole load of people at roughly the same time, about 3 or 4 years ago. So why does friction matter here? And why is the nature of the interaction, the contact friction interaction between particles, what's needed to understand these sudden changes in behavior? Okay, so let me say a bit about that. The dense suspension, as I showed in the movie, you have some kind of network which flickers in and out of existence of load-bearing contacts between these particles. And this is connected with a problem studied in the Victorian age, which is how many struts do you need to make the building not fall down. So that's the Forth Road Bridge, which is close to my heart. I've lived in Edinburgh for 20 years, under construction sometime in the Victorian age. So this, for whatever reason, I don't actually know why he was interested in this. This occupied James Clerk Maxwell in one of his idler moments when he wasn't solving electromagnetism and thermodynamics and most other physics of the day. So he asked, how many connections do you need for a rigid structure? And he immediately realized that this depends on the type of connection. In particular, if I have a fixed joint between two struts in my bridge, then I have a constraint of the length and the angle between each node, if you like, or the angle and so a fixed joint constrains angles as well as separations between the nodes. A hinged joint constrains only the length. And so a square is rigid if these are fixed, but if they are hinged, it is not rigid. A triangle is rigid either way. So translating essentially the identical conceptual physics into the problem of our dense colloidal suspension, we are drawn to the following question. What we have in a packing like this is we have a certain number of contacts per particle, and these contacts, the number of contacts per particle is strongly dependent on the density of the packing, hence on the concentration of particles. So I'm just, although it depends also on other things, I'm going to suppose that this is just a function of concentration. So in these, if I got my microscopic ping pong balls, they're touching, and some of them have friction, but some of them are sliding. So I can distinguish between a contact in which it's obliged by friction to roll. If I get the same two particles and I separate them a little bit, then they may be able to slide. So that question of separation will come back in a minute. But let's suppose, just for now, that I have a certain fraction of rolling contacts and the others are sliding. So there's this criterion, which I'll explain on the next slide, which says that when the number of contacts per particle is bigger, and this is in 3 dimensions, than 4f plus 6 times 1 minus f, and a different result in 2 dimensions, then this is rigid. So if I have sliding particles, I need 6 contacts per particle. If I have rolling particles, I only need 4. So what that means is there's a range of densities where the number of contacts per particle is in the middle here somewhere, where it's crucial as to whether they're frictional or whether they're rolling or whether they're sliding. And it's that transition which actually can control the unusual behavior of these very dense shear thickness suspensions. So let's just develop that a little bit more. So this is where the real theory is, other than just the curve sketching. This is to do with counting equations, not solving them. This is all Maxwell did, so we'll do the same here. N spheres, 3 dimensions, and I'm going to ask about the total number of forces, torques, equations, contacts, variables, and whether the backing is rigid. So let's just quickly go through this. So if the in 3 dimensions, if so what I have is at each contact. See if we can get this right. Yeah. So this is not a contact. So I have n particles. So I have to specify the force on each of those particles, and the force is a vector. So I have 3n forces that need to be in balance. They would need to vanish on each particle for the system not to be moving. That's true whether the contact is sliding or rolling. If I have rolling particles, I also have to balance the torques on a particle. So there are tangential forces at the surfaces, and they also have to sum to 0. So I have that many torques, which also have to sum to 0. If they're sliding, I don't have to worry about torques at all, because all the forces between particles are normal to the interparticle separation. So the torques drop out here. So this is the number of equations, if you like, the number of quantities that have to equal 0. I could also ask how many contacts I've got. That's the same in both cases. It's Z times n over 2. So each particle has Z contacts, Z, we're in North America, excuse me, and they're shared by 2 particles. So Zn over 2. And the number of variables, in other words, at each contact, I have this number of variables for the forces between particles. It's just 1 per shared contact if it's a normal force, because it's a sliding system. If it's rolling, I have to specify both tangential components of the force as well. So the criterion for rigidity is possibly slightly unintuitive. It's when the number of variables is bigger than the number of equations. And that actually kind of sounds like the opposite of what you think about when you can solve an equation. But the reason for this is a system is rigid if there are many static solutions to the equations of force balance. So if there's a multiplicity of static solutions, then the system cannot flow, because I can vary the forces and the thing stays static. If this is underdetermined, then it's essentially flowable. So if you just take a weighted sum of rolling contacts and sliding contacts, you get the criterion that I gave you on the previous slide.